So welcome to Artificial Intelligence Foundation and Application course. So today we'll look into temporal logic and its applications. So in the first part of this lecture, I'll be talking about how we can use this temporal logic to specify different properties of the system, because for certain system uh, where I need to introduce a timing notion, then I cannot use propositional logic directly. I have to enhance the modeling mechanism so that we can introduce the time notion there. So you have already seen the basic propositional logic, the first order logic, and there is no notion of time. So so for specifying the properties of system, uh, we often requires the notion of time, and we will not be able to use propositional logic in the normal form to solve those scenarios. So let us take a very simple example, which is almost our day-to-day example scenario. Like, let's say I have a car where I have a brake. So when I press the brake, so pressing a brake is an event. I can have I have an accelerator, so I can press that accelerator to increase the speed, or I may want to stop my car, or maybe I want to slow down my car. So let's say these four events are given to me, and and I would like to specify the system properties in this way. Probably when the brakes are pressed, the car slows down in the next instant. So the one difference here is that I would like to specify the next instance. So if you remember the normal propositional logic, then if brake is pressed and the car slows down, so I cannot say B implies D, then I am missing this next instant. Similarly, if you look into the second one, when no accelerator is pressed, then after a while car continuously uh, slows down. So how we can actually specify this continuous behavior, or some stuff that we will be able to specify in our modeling stuff. The third one, when brakes are constantly kept pressed and there is no accelerator pressed, the car slows down and eventually stops. So kept pressed, so I have to specify something, then the car slows down, so that is one thing, and another timing notion that we are introducing something like eventually it stops. So I have to have some mechanism through which I will be able to specify this kind of system on the properties. And the purpose of this kind of properties is like when we want to verify a system, because let's say somebody has designed the car, and the manufacturing company is claiming this kind of properties. So these are very naive one. So now if I want to really verify that this property really holds, then I have to check, and like the earlier step in propositional logic, what we have done, we model the problem using propositions, and we built the knowledge base, and then actually we queried on the part, and we checked whether certain thing is true or not. So similar stuff we want to do, but we need to introduce the timing notion here, so which is one of the major challenge in this case. So now let us look into few other stuff, like I said that verification is one of the major domain where we'll be requiring this stuff. So let us look into this problem very quickly. So let's say I want to verify combinational circuit, and I'm pretty sure you are familiar with what does the combinational circuit means. So let's say I have implemented my marks in this way, which has A select and B input line, and there is the output, and somebody else uses the same input line and produce another output but uses a different implementation altogether compared to this one. So if I want to verify this thing, what thing I can do, I can compute the Boolean expression for y1 and I can compute the Boolean expression for y2. Now if I do that stuff, then I will get two different expressions, something like these two things, because here it is implemented using NAND gate, here it is not an AND or gate. So I get two different expression, at least in the first go. Now I can use binary decision diagram based methodology, where if I try to represent this functionality in BDD form, then they will actually yield the same diagram. Provide there are some restriction, like you have to ensure that the variable ordering are the same, then it will lead to a canonical structure, and then we can actually verify that whether y1 and y2 are the same or not. So that is the very simple thing. Now when we go for a sequential circuit, so most of the practical circuits are actually sequential circuit, and the automotive system example that we have seen is also a sequential circuit, because it depends on the previous state and so on and so forth. So when we specify the properties, it's basically span across cycle boundaries. So that is one of the major challenge. Now let's say I have a round robin arbiter, and so the purpose is this, like there are two requests, R1 and R2, and the arbiter actually gives grant G1 and G2 in some way round robin fashion. So maybe the person who has designed these things can say that it tries to support this property. So if the request bit R1 is true in a cycle, then the grant bit G1 has to be true within the next two clock cycles. So if R1 is true in a cycle, then the grant bit G1 has to be true within the next two clock cycles. So that is the property. Now if I want to specify this thing, so I need some kind of a temporal logic to specify the behavior, because within the next two clock cycles that I have to specify, how am I going to specify that thing? So I need temporal logic for that, and that is the main idea for today's lecture of this part. Now in order to extend the idea of normal combinational circuit or the normal propositional logic, what we would like to do, we would like to visualize this arbiter. We would like to visualize this as in this way. We will unfold the circuit. So we have this sequential circuit, we unfold the stuff, and when we are doing this unfolding, we are just only noting down this R1, R2, G1, G2. So this are the R1, R2, G1, G2 values at t equal to 0 at time instant this one initial. Then similar value I will have at t equal to 1 as well. And I will have similar values for t equal to 2 and so on and so forth. Now if I want to specify the properties, like if the request bit R1 is true in a cycle, then the grant bit G1 has to be true within the next two clock cycle that I was taught. So now what we can say, like we can say in this manner, if we really want to go ahead with the propositional logic, or the main idea is that we would like to augment the propositional logic with this temporal notion. Now if I so when we unroll this circuit in this manner, then this variable R1 is not just a single variable, but this R1 has a time index. So every time I have R1 value, and I can say that this is actually R10, this is R11. So the variable, so I have a set of number of variables for for each individual variable in the original stuff. So, and now when we try to specify this thing, we can specify the properties using this set of variables that span across the time. So what we can say that R1T, that means the request bit 1, request 1 is true at some point of time. This actually implies that in the next cycle or in the next to next cycle, G1 has to be true. So only thing I'm specifying the properties across the time step, that is very much required. And also I need to say that this is true for any time step. It is not only for t, but it should hold for any time step. So so the overall idea is coming from propositional logic, but we have to introduce a notion of time in that logic. So so in the propositional logic, the time is actually implicit. Now when we try to extend this idea in this domain, then probably we can say that R1 implies that next of G1 and next G1. So if I introduce a special operator for next, then probably I can go ahead with the propositional logic, but this next will have some kind of a time notion, but as if the whole stuff will appear as a single variable, and then I can treat this one as my propositional logic, and we can exploit the results from that stuff. And for all t means I have to specify always this should hold. So so the idea is very simple. So we need to have some mechanism through which we can specify the temporal behavior. So when I have this temporal formula, something like this, then this looks like the normal propositional logic. So it will have either truth or the false value. So so the truth value of a temporal logic is defined with respect to a model. And the temporal logic formula is statically true or false in a given model. So if somebody gives me a model, and on that model I have to check whether a given formula is true or not. So this formula is actually statically true. Uh, so so this logic formula is not statically true or false in a model. So sometimes it can hold, sometimes it cannot hold. On certain part of the model it can hold. So there are a lot of things that we have to check. The models of temporal logic contain several states, and a formula can be true in some states and false in others. So so the thing is, in some part it can be true and some part it may be false as well. And in order to specify like this temporal idea, like which is very common in our normal life, I can say that I would like to specify that I am always happy, I will eventually be happy, I will be happy until I do something wrong, or the simple thing is I am happy. So these are some kinds of temporal stuff that we may need to specify, because I can have lot complicated queries, but in order to simplify the situation, I may be interested in some extreme case behavior. Probably this is true in the next time instance, probably certain thing is eventually hold, or it can be triggered by some event kind of stuff, or the normal stuff. So effectively we will try to portray this kind of properties in our model. And when we say we need a model, the model requires a Kripke structure, so which is similar to the finite state machine. Now and there are a few differences. So so let us look into what is there in there in the Kripke structure. So first thing, I have a set of states S, I will have set of initial state which is similar to the finite state machine, and I will have a transition relation. So from a given set, from a given state, I should be able to move to some other state. And apart from that, the extra thing that we will have in Kripke structure is a set of atomic proposition. So this the proposition that will be labeled to each state. So I will need a labeling function, and so this means that in this state P is true, and in this state PQ is true. So whatever has been specified on a given state, then those propositions is true, and whatever is not specified on a given state, then those are actually false. So that is the basic interpretation. And when I have a Kripke structure, another thing also will be required, that from a given state I will have some outgoing edge as well. It can come back to itself, but there will be some outgoing edge. And on this kind of model, you'd like to query those temporal formula, and we would like to see that whether certain formula is true in some state or not. That will be the main objective in this case. So given this Kripke structure, one of the thing when we would like to verify some properties being hold or not, then we would like to see whether this property holds across the states. And when I'm looking into across the state, that means I'm basically extracting out some path from my Kripke structure. So I have to find out a path, or a path in a Kripke structure is a sequence of states such that this holds. Basically from Si to Si plus 1 there should be some transition. So given this diagram, I can say this is one path, maybe this is another path, this is another path, and so on and so forth. And there are some terminologies. So this part will be called is the prefix of pi k. Similarly, this part will be called the suffix of pi k. So which are some terminology. Now the stuff that we need to really know is the set of temporal operators. So two most fundamental operators are the next and until. So what does the next operator say? It says that the property P holds in the next state. So that is XP. What is until operator? Until operator says like property P holds in all state up to the state where property Q holds. So it will be effectively something like P hold across certain states, and then I get a Q. So we'll elaborate those stuff with examples and the pictures in upcoming slides. The other derived operator that we'll have is something like eventual or the future operator. Like when I want to say that some properties is going to hold eventually, so that I would like to specify with some FP. Yeah, and there is another property like always on the globally GP, the property P holds always at all states. And all these operators are interpreted over the paths in the Kripke structure that we are actually considering. And all kinds of Boolean operators are supported by temporal logic, because the basic idea is our propositional logic, which has been extended with this temporal notion and these temporal operators, primarily these four temporal operators. So the next operators, which is basically if I'm looking into this state, then P must hold in the next state immediately. If I choose a path, then P must hold at this point. So this is the next operator, and there are formal definition, you can just follow it up. P until Q, what I was saying, like P holds the YOLO at the P, and then I got a Q. So it may happen that P is true at this place as well. So even if P is true, I do not bother. So I get a sequence where P is true, and then I'm getting a Q, because Q holds eventually and P holds until Q. So once Q holds, then we are not making any kind of a constraint that P should not hold, or P must hold. So effectively it will be like PQ, and in this state P can also hold. So that is not our concern. The eventual operator, so it is you can understand from the meaning, like uh, eventually it should hold, so it's not necessary in the next, but sometimes in the future, so that we specify with FP. And if we use this until operator, then we can specify the properties in this way: true until P. That means uh, if nothing is labeled, so I can say true is true in this state, so which is by default is true. So effectively it is true, 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 and then P. So P holds eventually. Global operator, again it is simple to understand, like in every state P will actually hold. So this can be actually written as true until not P and not of that, and also this can be written as not F of not P. That means not P does not hold in future. So this way we can actually model the stuff. Now when I have a Kripke structure, then it is interpreted over a model, and this model can actually unfold, and on the unfolded model, when we unfold the model, basically it generates a tree, and on that computation tree we would like to see whether this property actually holds or not. So something like, if I have a Kripke structure something like this, and when I want to interpret some formula over this architecture or over this model, it effectively boils down to I have to check on a computation tree something like this. So if you look into here, so it is AB, maybe from AB I can go to BC or I can go to C. So that is the situation. From BC I can go back to AB, or from BC I can go to C. So BC to AB, BC to C. From once I reach C, then I will continue in C. I have no other option. Fine. So and along with that, another thing will be required is like the path quantifier. So when we are looking, so till now what we are looking is a formula that is true over a path. So whenever I want to specify certain things, I am just looking, I am taking a path, and on that path whether a particular formula is true or not. Now in order to simplify a scenario, the two most important thing will be required, like I may not be able to I may not be interested in knowing everything, but I may be interested in knowing that along all paths certain properties is true, or there exists at least a path certain property is true. So effectively we would like to specify this thing as a path quantifier, like A and E. This basically means for all paths, and this basically means there exists a path. Now now when I have a path formula, like GP is a path formula, and when I add along all path or there exists a path, that means it becomes a state formula, because from a given state I would like to see whether all paths satisfy this property or there exists a path that satisfy this property. Now if I try to elaborate with some pictures, then when I have this universal path quantification, and if it is like AXP that I want to check whether this is true at this state or not, then this will be true if P holds here and P holds here, because XP is the path formula. So if you look into this path, then XP is true. If you look into this path, XP is true. Now in this state, AXP is true because along all path your XP is true. Similarly, if you have AGP, then along all path P is true, so P has to be true in every state. path when you have AFP, you are looking into at this state. So in this path P is true, in this path AP is true. So in both the in this path AP is true because there is a path and P is true on that path. And I'm not going to see into any nodes whether P holds or not, because if I take this path and I found P holds, then along that path definitely AP will hold. So I can say AP is true. AP until Q. So if you look into this path, so P until Q is true. If you look into this path, P until Q is true. If you look into this path, P until Q is true. So along all path, P holds until Q holds. Similarly, for existential quantification, if you have EXP, then there is a next state in which P holds. And similarly, EGPA, I need just only one path along which P should hold. I have EFP, then I should need to have just at least one path along which FP is true. And similarly EP until Q, so I need to have a path where PP and then Q. Now the stuff that we have talked about, like when we have this GPU, we told that it is not F not P, and that can be actually derived from the idea of De Morgan's law, and we can claim that there is a duality between always and eventual operator. So like we can say this GP is nothing but P and next P, next P, next P, and so on. Now if we apply we just introduce the negation and then apply the De Morgan's law, then it comes out to be this one. And if we reorganize the stuff, we get not F, not P. So computational logic is the main thing, the computation tree logic that we'll be looking into a little bit in more details later. So the idea is as follows. So given a set of atomic proposition and any Boolean formula over the atomic proposition have the CTL properties. So that is the basic definition. So if I have a Boolean formula only that does not span over time, still that will be considered as a CTL formula. Now let's say F and G are some CTL formula. If I have F and G that are CTL formulas, then any one of this will be my CTL formula. So what does it says? The negation of F, AXF, F until G, EXF, and EF until G. Those will be the CTL properties, and and properties like this can actually be derived from the stuff. Now now the thing is, when I write some formula, something like AXF, what does it actually mean? The semantics is as follows. For a property, the property AF is true at a state S of the Kripke structure if and only if the path property F holds on all paths starting from S. So when I specify any formula A, P, then I have to say that from which state, and by default it is interpreted that from the start state the property should hold, because when I'm specifying some property, it is expected that from the start state the property should start hold. So F is the path property, and when I make it AF, then it becomes a state property. Similarly for EF, when this will be true at a state S if and only if the path property F holds on some path starting from S. So now let us look into few examples. So the thing is, when I have this formula, this is simple, and I can have nested formula. So I would like to explain with this examples. So when I have a nested formula like ax agp, it means from all the next state p holds forever along all paths. So in order to interpret this one, so p holds along all path. Uh, so this AGP means the p holds globally along all path, and this AX means along all path from the next state AGP should hold. So effectively, if I'm looking into this state, then from this so so if I'm looking into this state, then AX AGP should be true here. That means AGP should hold in the next state. In this state, AGP should hold in the next state. So if we look into this part of the tree, then I can actually claim AGP is true because P is true here, P is true, P is true. Similarly for this part, so AGP is true in these two states. So I can claim AX AGP is true in this state. Similarly, EX EFP, so there exists a next state from where there exists a path to a state where P holds. So there exists a next state, and there exists a path to a state where P holds, EX EFP. And we can make a more different kind of nesting with A and E properties, AG-EFP. So along all path globally EFP should be true, and EFP can be true if along the path P is true in some state. So if you look into this one, P is if P is true, if P is true, and if you took any other path, AP is true and EFP is also true. So along all path I can actually say AGEFP is true. So with this stuff I will stop now. We will look into more examples in the next part of this lecture. Thank you.